Yes, I do.
All right. So all the problems we were doing yesterday with these volumes, we were doing it in terms of x. That meant that my variable was x, it had a dx at the end, and the limits had to be x values. And we went from left to right. But sometimes it's really hard to do it in terms of x. So in that case, we can do it in terms of y. If we do that, the variable has to be y, we have to have dy at the end, and the limits have to be y values. Think bottom to top if you're going to do that. So let's take a look at this one. If I asked you to find the volume of the solid obtained by rotating the region bounded by y equals x cubed, y equals 8, and x equals 0 about the y-axis. So if I draw a picture. What's x cubed look like? A chair. Okay, so this is my curve. But then I put some limits on it. Y equals 8, that's just a horizontal line, right, at 8. So it's bounded by that, so I know we're cutting it off there. X equals 0. So that means I'm not looking at the negative side. I'm taking just this portion. Hello? Got it?
Yeah.
Thank you. I was expecting worse condition, honestly. All right. Here's why this one is hard to do in terms of x. Because I'm going to rotate it around the y-axis. Yesterday, we were rotating around the x-axis. And that's why we had a clear left and rightmost point. If I rotate this around the y-axis, so it would end up looking like this. Do we have a clear left and rightmost point? Kind of, I mean, we have like the furthest, but it does vary depending on where you're at, right? So if you're rotating around the y-axis, that's a good time to work in terms of y. If you're rotating around the x-axis, that's a good time to work in terms of x. If I'm going around my y-axis, do I have a clear lowest and highest point on this graph? Yeah, my lowest is 0, my highest is 8. Okay, if I think about a cross section, so if I slice this, since we're rotating around the y-axis, think about slicing perpendicular to that. So it's circular, right? Area of a circle is pi times the radius squared. And we're working in terms of y. We've already decided, so it has to be dy at the end. My variable has to be y. So the radius of that piece, the radius would be from here to there. And I know that is x cubed. But here's the problem. If I put in x cubed, what's wrong with that? That's in terms of x, not y. So if I wanted to solve this in terms of y, what would I have to do? So x is the cube root of y. So instead of putting x cubed here, I could put cube root of y. And again, we only have to do that because we're rotating around the y-axis. So it's easier to work in terms of y. So our variable has to be y. Any questions on that part? The setup is the tricky piece. Now, we can take out the pi if we want. This is like the cube root, so 1/3 power squared, so that would be 2/3. So if I add 1, 5/3 power, so we have 3/5 in the front. Okay, so the cube root of 8 is 2. 2 to the 5th is 32. Cube root of 0 is 0. 2 to the 5th is 0. We get 96 pi over 5. problems that we've done so far, whether we did it in terms of x or y, we are basically taking a curve and rotating it around an axis, okay? We talked about yesterday, all of those problems had a function in terms of x rotating around the x-axis. Anytime you do that, what shape is your cross-section? Circle. And so then we're really doing all these problems the same. The area of a circle, we know, is pi times the radius squared. And if you're just rotating around the axis, the radius is just your function squared. And so that's really how we've done all of those. This has a special name. It's called the disk method. So if you are rotating around an axis, okay, key thing being the axis, either an x or a y, you can find the volume by just doing pi times the function squared. All right, let's look at this one. Find the volume of the solid formed when the region enclosed by the curves y equals x. What's y equals x? Straight line. Okay, slope is 0. Or sorry, y-intercept is 0, slope is 1. And then y equals x squared is a parabola. 0 squared is 0, 1 squared is 1. You can find more points. Okay, this is my rough sketch. If you weren't sure about those intersection points, so if your graph wasn't accurate enough to find them, we said the region enclosed, so we're looking at when those things are equal. So you could always, if you can't tell from your graph, work it out. So we get that it's 0 and 1. I am rotating around the x-axis. So am I going to work in terms of x or y? X. Okay, I have my intersection points for x. We're going from 0 to 1. And we said we're working in terms of x dx. Okay, here is my curve. I'm only talking about the region between them. So if it confuses you, you can get rid of the rest of the graph. All we need is this little piece. And I'm rotating that around the x-axis. Now my drawings are not great. So for me to draw the rotation, I just think of it as a reflection. And then spin it. So what we have is kind of like a funnel. Flip on its side. So here's the thing. If I set it up going from 0 to 1, if I just did the outside was y equals x. Okay. If I look at these cross sections, the cross section is what shape? Circle. But when you actually take it and stare down at it, it's not solid, is it? It's going to look like a donut. We're going to have something around the outside and then hollow in the center. So what we're going to have to do is take the outside one minus the inside one, because we have to subtract off what's in the center. All right, what is my outside function then? Y equals x. So we're working in terms of x. So we're going to do the outside radius squared minus the inside one is my parabola x squared squared. Okay, each of those gets a square. We're doing basically the entire volume of the outside minus the entire volume of the inside. All right, so volume pi times the radius squared. So you square the outside one minus square the inside one. X squared minus x to the 4th. Antiderivative of x squared is 1/3 x cubed. Antiderivative of x to the 4th, 1/5 x to the 5th. Plug in 1. put in a 0, I get a 0. So we have an overall volume of 2 pi over 15. So this one was a little bit different because it was hollow on the inside. The reason that happened is I had 2 different functions that were being rotated. So anytime you have 2 functions being rotated around the axis, when you look at the cross section, what's it going to look like? A donut. Okay, it'll always, they're both circular because we know if you rotate a function around the axis, it creates a circular shape, but it'll be a donut. It'll be hollow in the center because we have those 2 functions. So that's what's called the washer method. So you're essentially just doing volume of the outside minus volume of the inside. Easier way to set it up is just outside radius squared minus inside radius squared. All right. So I want the volume of the solid obtained by rotating the region in example 6a around the line y equals 2. So I'm changing the game a little bit here. So it's the same one we just did. So we had our line, and we had our parabola. Okay, same region. But this time, I'm not rotating around an axis. I'm rotating around y equals 2. What's y equals 2? What kind of line? Horizontal line. All right, so if I were to draw this, here's y equals 2. Okay, for me to draw it, I have to think of it as a reflection first, so this is one way from the line, this is one the other direction. Got that line. Parabola. Taking this. Okay, we're still getting our donut shape, but it looks a little bit different. All right, I told you that if we rotated around the x-axis, we did it in terms of x. If we rotated around the y-axis, we did it in terms of y. Think of it as horizontal and vertical lines. The x-axis is a horizontal line. So if you're rotating around a horizontal line, you want to keep it in terms of x. That will be your easiest bet. We can see that here. It is still very obvious what the smallest and biggest x values are. The y values kind of switch depending on where you're at. So we are going to work in terms of x. So we're still going to go from 0 to 1 for our x values. So everything's in terms of x. But here's where it gets a little bit tricky. We have to have the outside radius squared minus the inside radius squared. So if you take a cross section, which one's on the outside? The x squared. Now, it's not just the function anymore though, is it? The radius is going to go from here to the edge of this. So I can't just say the radius is x squared because I didn't rotate around the axis. If I were measuring this radius, it starts at 2, and we would have to subtract x squared to get the distance between them. Radius is 2 minus x squared. And that has to be squared for our volume piece. Okay, the inside one. So if you're talking about that inside radius, we're talking about starting at 2, and it has to go down until we get to x. So that one is 2 minus x squared. So again, the reason these are different is we didn't rotate around the axis. We rotated around a different horizontal line. So personally, before I did this antiderivative, I think I would multiply it out. So if I square that, I get 4 minus 4x squared plus x to the 4. And this is going to be 4 minus 4x plus x squared. So 4 minus 5x squared plus 4x, and my 4's cancel. What's the antiderivative of x to the 4? Antiderivative of 5x squared. 3x cubed, and antiderivative of 4x. So we have a few examples left. We are going to do those tomorrow. Remember yesterday I gave you a handout. And yesterday I recommended that you do question 1, 2, and 3. Today I'm going to recommend you do 4, 5, and 6. All of those are just rotating around an axis. Okay, tomorrow we will do another example where we're rotating around something that is not an axis, and then you'll be able to finish the last ones. So technically you have all the knowledge you need. You could do all of them. But try to have at least 6 done tomorrow, so we're kind of staying on track and not cramming at the last minute to get our homework.